In this video, we're going to talk about a type of differential equation that's known as separable. A differential equation with independent variable x and dependent variable y is called separable if it can be written in the form you see here. dy dx is equal to the product of a function of x times a function of y. It's called separable because you can separate the variables. Let's talk about the method here that we can use to solve this differential equation. The method is to treat the derivative dy dx as a fraction. dy dx is not a fraction, it's a derivative. However, for this method, we're allowed to pretend that it's a fraction. So that is, we're imagining that dy is a quantity that's divided by another quantity, dx. It isn't, but we're just going to pretend. Why does that help us? We have dy dx is a function of x times a function of y. So what we're going to do is we're going to separate the variables. That is to say, we're going to get all of the y's on one side and all of the x's on the other side. So I'm going to divide by gy. So we're going to have 1 over gy, g evaluated at y, dy dx is equal to f of x. And the next thing to do is to multiply this dx over to the other side. So we have 1 over g of y dy is equal to f of x dx. And the next thing to do is to integrate both sides. The left side we integrate with respect to y, and the right side we integrate with respect to x. So first, you separate the variables. That's what we're doing in these steps, these first steps. Separate the variables. Then we integrate both sides. And finally, whatever the result is your answer. So you solve for y as much as possible. We'll see several examples so we can understand how this method works. This technique, this method that we're using, is a trick in the sense that we're treating dy dx as a fraction even though it's not. Really, there's something a little more complex going on. So if we wanted to explain what's really happening, we still start with dy dx equals f of x g of y. And then you still divide by that g of y. So you have 1 over g of y dy dx equals f of x. And then you still integrate both sides, but you integrate both sides with respect to x. So the integral with respect to x is equal to the integral with respect to x. Now on the right, this is exactly the same as above. The one on the left looks a little bit different. Again, if you're treating dy dx as a fraction, then the dx's cancel. But you can't really do that because dy dx isn't a fraction. But you can use substitution to undo what's really happening here, which is the chain rule. So if you let u be equal to y, then du dx, or rather du I should say, du is equal to dy dx dx. So really what's happening on the left here is that you have the integral of 1 over g of u times this expression, which is du. And this is the same thing as what we had before. So it's the same as before, but using u instead of y. And that's okay because as you can see, u is equal to y. They're actually the same. So what's going on here is really a substitution. We just use this trick pretending that dy dx is a fraction because you get the same thing either way. But keep in mind that there is something else going on here. In fact, what you're doing is using a substitution to make it look like you have a function of y that you're integrating with respect to y on the left, whereas really you have a composition that you're integrating with respect to x, and that's what you see here. Really, you're undoing the chain rule. However, the effect is the same, so as a technique, as a tool, we just pretend that we have a fraction. So that's the method. Let's actually use it for some examples so we can see how this works. Here's our first example. Solve the differential equation here. dy dx equals x times e to the negative y. This has the right form. The derivative dy dx is equal to a function of x times a function of y. F of x equals x, and g of y equals e to the negative y. So this is a separable differential equation. So what do we do? Let me just rewrite it here. The first thing we do is we get all of the variables on separate sides. All of the y's go to the left and all of the x's go to the right. So we divide by that e to the minus y, or if you prefer, you multiply by e to the y. So e to the y dy dx equals x. And then you put that dx over on the other side. So you have e to the y dy is equal to x dx. And then you integrate both sides. On the left, you have the integral of e to the y dy, which is going to give us e to the y, plus some constant, but we'll save that for now. On the right, we have the antiderivative of x, which is x squared over 2 plus a c. We don't need to put a plus c on the left, because if we did, we'd call it c1, and we'd call the other one c2, and then you'd write e to the y is equal to x squared over 2 plus c2 minus c1, and then you can just call those c. So you don't need to write c1 and c2. So we don't need both constants. So instead, you just write e to the y equals x squared over 2 plus a constant. This is what we call an implicit solution. So this is the solution in implicit form. Implicit as opposed to explicit. An explicit solution is y equals some function of x, and we can get that here. If you take the natural logarithm of both sides, on the left you have the natural logarithm of e to the y, and on the right you have the natural logarithm of e squared over 2 plus c. There's nothing you can do to simplify that, at least not practically. On the left you have the natural logarithm of e to the y, which is y. So what you have is that y is equal to ln x squared over 2 plus c. This solution is in explicit form. An explicit solution says that y is equal to some function of x. An implicit solution tells you that there is a relationship between y and x. But perhaps you can't explicitly say so. If you can solve for y, then solve for y. If it's possible to write down the explicit solution, you should do so. Otherwise, the implicit solution would be sufficient. But now here we have our explicit solution, which is y as a function of x. Notice that there's a plus c here. There are an infinite number of solutions. Let me fix that plus c. Let me also fix the 2. There are an infinite number of solutions, and each different value of c gives you a different solution, but they're all in what you'd call the same family. They're all related because they all just have different values for that c. But notice that the c is inside the natural logarithm. It started out as a constant of integration, but then we solved for y, and we took the natural logarithm of both sides, and then the c ended up inside the natural logarithm, and that's not uncommon. Usually when you're doing this kind of problem using separation of variables, your constant, which starts off as a constant of integration, will end up in some sort of strange place, either inside a logarithm, or in a denominator, or in an exponent, something like that. So let's do another example. Here we have a differential equation where u is a function of t. So now t is our independent variable and u is our dependent variable, but we approach it the same way. This differential equation is separable because we're writing the derivative as a product of a function of u times a function of t. So du, that's supposed to be a u, du dt is a function of the dependent variable times a function of the independent variable. So we would say that f of t is t and g of u is u. So it's a product of a function of the independent variable and the dependent variable. So the first thing to do is to separate the variables. So we divide by u, and that's going to equal t. So we're going to integrate both sides by t, but using our trick, we pretend that this is a fraction and we multiply by dt, or we just write the dt over on the other side. So we write 1 over u du equals t dt. And now we integrate both sides. On the left side, we have the antiderivative of 1 over u, which is going to be the natural logarithm of the absolute value of u, plus a constant, but again, we'll save the constant for later. On the right side, we want the antiderivative of t, so that's going to be t squared over 2. And then we write plus our constant of integration. At this point, we want to solve for u. The first thing to do is to exponentiate both sides. E to the ln of the absolute value of u is equal to e to the t squared over 2 plus c. On the left side, you have e and ln canceling, so you just have the absolute value of u. This is going to be equal to e to the t squared over 2 plus c. Now one thing that we can do is we can write this as e to the t squared over 2 times e to the c. If you multiply two exponentials together that have the same base, the effect is that it's the exponential to the exponents added together. So since these two have the same base, we add the exponents together to get t squared over 2 plus c. Why would we do that? Well, notice that this is some constant e to the c times e to the t squared over 2. C is an arbitrary constant, so e to the c is also pretty arbitrary. Notice e to the c is necessarily positive, but this is a positive constant. It's an arbitrary positive constant because c could be anything, which means e to the c could be any positive number. E to the c can't be 0, e to the c cannot be negative, but it can be any positive number. We have that the absolute value of u is equal to e to the c times e to the t squared over 2. That means that this quantity is either positive or negative, so u is positive or negative e to the c, e to the t squared over 2. Here we have e to the c, which is any positive constant, and we have a plus or a minus in front. We don't know which one. But that just means that we have some constant here, some non-zero constant. e to the c cannot be 0. So we have some non-zero constant, but otherwise it's completely arbitrary. So it's very common to just give it some other letter as the name. So we might say that this is just equal to a times e to the t squared over 2, where a is equal to plus or minus e to the c. So a is some arbitrary non-constant, non-zero constant, that is. So a is any non-zero constant. And so what this tells us is that we have a solution in explicit form. So our solution that we obtained using this method is u equals a times e to the t squared over 2. Just to make it clear, this t squared over 2 is all in the exponent, so let me write it a little bit more carefully. T squared over 2, where a is just simply non-zero. That is the solution that we got using this method of separation of variables. Using this method, separation of variables, we obtain these solutions where a can't be equal to 0, but that does not mean that you don't have a solution when a is equal to 0. Notice what happens when a is equal to 0. So if a is equal to 0, then u is going to be equal to 0 times this exponential, e to the t squared over 2. But if you're multiplying by 0, you just end up with u equals 0. It turns out that this is a solution. So fact, u equals 0 is a solution to the differential equation. And we can verify that by just looking at the original differential equation. Let's do that. The original differential equation is du dt equals u times t. So let's just write that here. Differential equation. Du dt equals u times t. Now if u is equal to 0, we can show that this is a solution to the differential equation by showing that the left side equals the right side. Du dt is the derivative with respect to t of 0. Of course, the derivative of 0 is 0. That's the left side. And what about the right side? The right side is u times t, which is 0 times t, which is 0. So these are the same, or equal if you prefer to say it that way. So the left side of the differential equation is equal to the right side of the differential equation when u equals 0, so u is a solution when u equals 0. So why is u equals 0 a solution even though we didn't get it using our original method? When we used separation by variables, we explicitly got a solution that said we have a solution u equals a times e to the t squared over 2, but not when a is equal to 0. Why is that? Why did we seem to lose that solution y equals 0? The answer comes from our very first step. If we scroll back up to where we began this problem, our very first step, so here's the differential equation, du dt equals t times u. Our very first step was to divide by u. If you divide by u, then you're assuming that u does not equal to 0, because you're not allowed to divide by 0. So let's write this down. So remark, our first step when solving the differential equation du dt equals u times t was to divide by u. 1 over u du dt equals t. When you divide by u, you are making an assumption. That u is not equal to 0. So you have to check separately to see if u equals 0 is a solution. You have to make a separate check whenever you divide by some function of u. So in general, we start with a differential equation, dy dx equals some function of x times some other function of y. And our first step, let me write it that way, our first step is to divide by not by dy, but by g of y. So you have 1 over g of y dy dx equals f of x. That means you're assuming that it isn't 0. Assuming that g of y is not equal to 0 when you do that. So you have to check, so you must check to see if g of y equals 0 is a solution. In our first example, this didn't show up. Let's go back to our first example. Our first example is here. dy dx equals x times e to the negative y. What we did is we divided by e to the negative y. And e to the negative y can never be 0. So there's no extra solution that we lost. Because when you divide by e to the negative y, or multiply by e to the y, you're not losing a solution. You're not assuming something can't be 0 because it can't be 0 anyway. However, in our second example, dy dt equals ut, we divided by u, but it's certainly possible for u to be equal to 0. So when you divide by u, you're saying, I'm going to assume momentarily that u can't be equal 0, so that way I can divide by it. And then you do the solution. But this whole solution is predicated on the assumption that u was not equal to 0. That's why when we had our solution here, it said u is equal to whatever you've got, a times some function of t, where a is not equal to 0. Because you're assuming, way up here at the first step, you're assuming that u isn't 0. And that's reflected here in our solution. A not being equal to 0 means that u is not equal to 0. But you have to check separately. Well, what if u was equal to 0? I'm assuming that u isn't 0, but what if it was? What if u was equal to 0? And it turns out that u equals 0 is a solution. Sometimes you'll get a solution that way, sometimes you won't, but you always have to check. Let's do another example. Here we have an initial value problem. So remember what an initial value problem is. A differential equation together with an initial condition. So here, this is our differential equation, right here. And y of 1 equals 2, that's our initial condition. For the time being, we can ignore the initial condition. That will come later. The first thing to do is to solve the differential equation. dy dx equals, and I'm going to write it like this, ln of x over x times 1 over y. I've written it like this so we can see that there's a function of x times a function of y. What I want to do is I want to separate the variables. And the first thing that I do is I divide by 1 over y. Notice that that can never be equal to 0, so we're not going to have to worry about any extra solution. So really we multiply by y. So we have y dy dx equals ln of x over x. And again, I've divided by 1 over y, divide by 1 over y, but g of y equals 1 over y is never 0. So that means we're not ruling out any extra solutions. So the next thing to do is to write this dx over to the right. So we're going to have y dy is equal to ln of x over x dx. And now we integrate both sides. On the left, we have y squared over 2 plus a constant, but we can reserve the constants for later. And this is going to be equal to the integral on the right. The integral on the right, perhaps you'd prefer to write it as ln of x times 1 over x dx. We can use a substitution here. If u is ln of x, then du is 1 over x dx. So this integral is going to be u squared over 2 plus a constant. So u in this case is ln of x. So ln of x quantity squared over 2 plus a constant. Now this is our implicit solution here. That's our implicit solution. And at this point we can figure out what c is, because now we have a relationship between x and y. Our initial condition says that y is equal to 2 when x is equal to 1. So that means the point 1, 2 is on the solution, is on the graph of the solution. The graph of the solution. Well, here's our solution in implicit form, but we can still solve for c. So we let x be equal to 1 and y be equal to 2, and we're going to have 2 squared is 4 over 2 is equal to ln of 1 quantity squared over 2 plus c. ln of 1 is 0, so this whole thing is 0. 0 squared over 2 is 0. And on the left, we of course have 4 over 2 is 2. So that tells us that 2 is equal to c. So we can plug that in right there. So now we have y squared over 2 is equal to ln of x quantity squared over 2 plus c. And again, this is our implicit solution. The first implicit solution is the implicit solution to the differential equation. The second implicit solution here is a little bit more specific because we know now what the value of c is, although I forgot to write it in. This is 2. This is the implicit solution not just to the differential equation. This is the implicit solution to the differential equation that also satisfies the initial condition. So this is the implicit solution to the initial value problem. IVP is how we usually abbreviate initial value problem. IVP. It is possible to explicitly write out this solution. The first thing you do is you multiply everything by 2. Y squared equals ln of x quantity squared plus 2 times 2 is 4. And so y is equal to the square root. Well, it should be plus or minus the square root of ln of x squared plus 4. That plus or minus means that we still have an implicit solution. An explicit solution means that you've written y as an explicit function of x. Right now it's not an explicit function because plus or minus means you haven't made up your mind. Is it plus or is it minus? It's not a function until you've decided what the output is. Remember that a function takes in one input and gives you out one output. There can't be any ambiguity there. Right now we have a plus or minus, so there's some ambiguity. But we can figure this out because we know that y is positive. Y is equal to 2. Y is equal to 2. That's a positive number. So that means you choose the positive sign. So y equals the positive square root of ln of x squared plus 4. And this is your explicit solution here. That's the explicit solution. If our original initial condition had a minus in front of the 2, so if our original initial condition said y of 1 is equal to negative 2, that means that our y would have to be negative. And in that case, you choose the minus sign down here. So if our initial condition had been a negative y, then this y would have to be negative as well. So then there would be a minus sign there. But since our initial condition had that y was positive, we choose the positive sign on this radical. And there we have our explicit solution. Let's do another example of an initial value problem. Here we are. Solve the following differential equation. Again, it's not just a differential equation, there's also an initial condition. So solve the following initial value problem is what it should say. So again, we have a differential equation here and an initial condition here. You start by ignoring the initial condition, at least temporarily. Just solve the differential equation. dp dr is the square root of p times r. At the moment, this is not written in the right form to be separable, but it can be written that way. It needs to be written as a function of the independent variable times a function of the dependent variable. And here we have that, but it's just underneath a radical, but that's easy enough to fix. You just write this as the square root of p times the square root of r. And now it's a function of p times a function of r. In this particular case, r is the independent variable, so this would be our f of r, and p is the dependent variable, so that would be our g of p here. That would be that. So in other words, we have dp dr is equal to a function of one variable, p to the 1/2, times a function of the other variable, r to the 1/2. And now we can separate this. We need to get the p on the other side, so you divide by the square root of p. So this is going to be 1 over p to the 1/2 dp dr is equal to r to the 1/2, or the square root of r. The next thing to do is to put that dr over on the other side. So we're going to have 1 over p to the 1/2 dp is equal to r to the 1/2 dr. Now notice we divided by p to the 1/2. Let's write this out. We divide by the square root of p. This can be equal to 0 when p is equal to 0. So this can be equal to 0. So we must check later to see if p equals 0 is a solution. Because square root of p equals 0 means that p is equal to 0. Now, we can actually just look at the differential equation and say, oh yes, p equals 0 is a solution. Because if p is equal to 0, then the derivative of that constant is going to be 0. And also, if p is equal to 0, then 0 times r is 0, and the square root of 0 is 0, so yes, it is a solution. Yes, p equals 0 is a solution. So let's set that aside for now, and we'll come back to it later. Right now, we're looking at this equation. 1 over p to the 1/2 dp equals r to the 1/2 dr. We integrate both sides, like so. On the left, we have the integral of p to the negative 1/2 dp, and that's equal to the integral on the right, which is the integral of r to the 1/2 dr. On the left, we use the power rule. You add 1 to the exponent, and then divide by that new exponent. On the right, you add 1 to the exponent, and then divide by that new exponent. We need a constant of integration, so we just put 1 in there. All right, well, on the left, this is 2 times the square root of p is equal to 2/3 times r to the 3/2 plus c. We can divide everything by 2. Square root of p is equal to 1/3 r to the 3/2 plus c over 2. Now, this is just an arbitrary constant over 2, so half of an arbitrary constant is still an arbitrary constant. However, let's remind ourselves that this is an initial value problem and we have an initial condition. So what we can do is we can plug in r equals 1 and p equals 3 to solve for c. So p is equal to 3, so that's the square root of 3 is equal to 1/3 times r is 1 to the 3/2 plus c over 2. Well, 1 to the 3/2, that's just 1. So 3 square roots of 3 equals c over 2. That's not quite right. Let me try that again. Let's write it all out. Square root of 3 is equal to 1/3 plus c over 3. So now we can c over 2. So now we can subtract square root of 3 minus 1/3 equals c over 2, and now we multiply by 2. So 2 square roots of 3 minus 2/3 equals c. That's our c value. And we can just plug that in right there. But also, we want to square both sides so we can get p. So p, well, let's just write it like this. Square root of p is equal to 1/3 r to the 3/2 plus c, which is 2 square roots of 3 minus 2/3 over 2. And now let's square both sides. So we have p is equal to 1/3 r to the 3/2 plus, and that 2 will cancel with these 2's here using distribution. So we're going to have square root of 3 minus 1/3. Quantity squared, and that's your explicit solution. Up here, that's an implicit solution. In fact, so is that. That's also an implicit solution. Once you solve for p as an explicit function of r, then you have an explicit solution. And that's what we have here. You should always write out an explicit solution if it's possible. There may be an occasion where you can't explicitly solve for your dependent variable, and then you just leave it in the implicit form. But if you can solve for an explicit function, you should try to do so. So that's our example. Now, keep in mind that we had another solution lurking around, which is when p is equal to 0. However, that does not satisfy our initial condition. Our initial condition is p of 1 equals 3. In particular, p is equal to 3. So p equals 0 is the solution to the dE. So p equals 0 is a solution to the dE, but not the initial value problem. So that means we don't need it for our solution here. But this is our solution to the initial value problem here. There we are. Let's look at one more example. This is an example of what is called an integral equation. Integral equations are closely related to differential equations, and their objective is essentially the same. You have an equation that involves an unknown function, and you want to find the solution, which is the function that makes it true. Here we have that y of x is equal to 3 plus an integral from 1 to x of y of t over t dt. Where here we're assuming that x is greater than 1. Well, actually it should be x is greater than or equal to 1, because it's quite fine to have x be equal to 1. Let me just fix that. There we are. In fact, it's very useful to know that x can be equal to 1, because when x is equal to 1, we have, what do we have as a result? That y of x is y of 1 is 3 plus the integral of 1 to x, but x is 1, y of t over t dt. Even though at this point we don't know what y is, we do know that any integral from 1 to 1 is 0. So this is 0. So y of 1 is 3 plus 0, or 3. So this integral equation comes pre-equipped, so to speak, with an initial condition, namely that y at 1 is equal to 3. So this is an initial condition. If we had a differential equation, we'd have an initial value problem that we could solve. And in fact, the integral equation does give you a differential equation if you just differentiate both sides. So the left side becomes the derivative of y. And on the right side, we have the derivative with respect to x of 3 plus the integral from 1 to x of y of t over t dt. So if you have your initial equation here, if you know that y is equal to that thing on the right, then if you differentiate both sides, you should still get the same thing. Because if two quantities are equal, then their derivatives have to be equal as well. So what does this look like as a differential equation? Well, on the left, you have the derivative of y. Well, normally we write that as dy dx. What about on the right? Well, the derivative of 3 is 0. So it's going to be 0 plus the derivative with respect to x of the integral from 1 to x y of t over t dt. That's supposed to be a t. And now we just remind ourselves of the fundamental theorem of calculus. The fundamental theorem of calculus tells us what this is. If you differentiate an integral from 1 to x, you just end up with the integrand again, but just replace the t's with x's. So this is going to be y at x over x. So dy dx is equal to y over x. This is y as a function of x. It's not y times x. We're saying that y is a function of x. So we just write that down as y here. But notice that this gives us a separable differential equation. And we can solve it. The first thing to do is divide by y. 1 over y dy dx equals 1 over x. We're dividing by y, so we're making an assumption here, and that assumption is that y is not equal to 0. So we have to ask ourselves, is it possible for y to be equal to 0? Would that be a solution to this differential equation? And sure enough it is, but is it a solution to our initial value problem? And no, it's not, because our initial condition is that y of 1 is equal to 3. So it is true that y equals 0 is a solution to the differential equation. And when I say the differential equation, I'm talking about this thing right here. Because you'll notice if y is equal to 0, then the derivative of 0 is 0, and 0 over x is 0. So yes, y equals 0 is a solution to the differential equation. But it does not satisfy the initial condition. Because the initial condition is y of 1 equals 3. And if y is equal to 0, it's certainly not equal to 3. So we don't have to worry about this additional solution. It is a solution to the differential equation, but not to our initial value problem. So here we are with our differential equation. The next step, just write a dx over there. Remember, dy dx is not a fraction, but we're just treating it like one because it's a bit of a shortcut. We integrate both sides. On the left, you have ln of the absolute value of y, and on the right, you have ln of the absolute value of x plus a constant. Now remember, x is greater than or equal to 1, so we don't need the absolute value there. We assumed, it's not so much that we assumed, but the problem specified. Let's write it that way. The problem specified that x is greater than or equal to 1. So that means the absolute value of x is equal to x. So we don't need the absolute values there. ln of the absolute value of y, we do need the absolute values there, because we don't know anything about y at this moment. ln of the absolute value of y is equal to ln of x plus a constant. Now, at this point, we can already figure out what c is, because we know that y of 1 is equal to 3. So what that means is y is equal to 3 when x is equal to 1. So we can plug that into here to solve for c. So we have ln of the absolute value of 3, which is 3, is equal to the ln of 1, which is 0, plus a constant. So that just tells us that ln of 3 is equal to c. So now we know exactly what c is. So we can plug that right in there. So ln of the absolute value of y is equal to ln of x plus ln of 3. If you want to simplify this, you can, because the properties of logarithms tell us that this is equal to ln of 3x. Even if you don't simplify that here, it would come up at the next step, because now we can exponentiate both sides. E to the ln of the absolute value of y is equal to e to the ln of x plus ln of 3. And you see that you can write as e to the ln of x times e to the ln of 3. And the first one becomes x, and the second one becomes 3, so you just end up with 3x, which is what you'd get if you exponentiated ln of 3x. So on the right, we have 3x. On the left, you get something similar. Namely, you get e canceling out with ln, and you just get the absolute value of y. So the absolute value of y is equal to 3x. So that means that y is either plus or minus 3x, but we actually know that it's not the minus, it's the plus, because y is equal to 3 when x is equal to 1. If we chose the minus sign, or the negative sign, we would have y equals minus 3x. However, that does not satisfy. So this does not satisfy the initial condition. So that means you don't choose the negative sign. So choose the positive sign. And then you have that y is equal to 3x. And this is the solution to your differential equation, and so it is also the solution to the original integral equation that you see here. So now we have our solution. And this is an explicit solution, as you can see.